So the first thing I'm going to do is sketch. And as I've hinted at in the outline here, we're not going to do a perfect sketch. We're going to do an approximate sketch. This will probably be the most work among any of these operations. Parallel comparison is actually quite easy. Sketching is, I think, the biggest insight in fusion trees. So, perfect sketch takes just the bits you care about. Okay, that we need. We only want to look at the bits we care about. But it's easy to look at the bits we care about. We can apply a mask and just and out the bits we care about. Everything else we can zero out. So that's easy. The hard part is compression. Taking these 4 bits and making them 4 consecutive bits. But they don't really need to be consecutive. If I added in some zeros here in a consistent pattern, that would still work. I'd still preserve the order among the sketches, and that's all I care about. And this is where I'm going to use the slop I have, because right now I have w to the 1/5 keys. If I did perfect sketch, the total number of bits would only be w to the 2/5, but I can go up to w. So what I'm going to do is basically spread out the bits, the important bits, in a predictable pattern of length w to the 4/5. Predictable just means it doesn't depend on what x is. So when there are extra zeros here, that's fine. But there's always going to be 2 zeros here, 1 zero here, 3 zeros here, no matter what x was. As long as it's predictable, I'm going to preserve order. And as long as it's length order w to the 4/5, if I take w to the 1/5 of them, that will still fit in a constant number of words. Because it'll be order w bits total. So that's what I can afford. And now I'm going to do it. So here's how. First thing, as I said, is we're going to mask the important bits. I just want the important bits. I should throw away all the others. And so this is going to be x prime equals x bitwise and here's where we're going to use the notation that the bits count from the right. I want the bith bit to correspond to the value 2 to the bi. Okay, this thing is just a bit string. Okay, it has 1s wherever the important bits are. So if this is b0, b1, b2, and b3, I just want this bit string, which is, you can think of this as 1 shifted left bi times. So I get 1s in exactly the positions I care about, and if I bitwise and that with x, it zeroes out all the other bits. This is what we call masking. Okay, so that's the obvious thing to do. And then the second idea is multiplication. And it's just like, well, maybe we could do it with a multiply. And then we'll just work it out, and the answer is yes, you can do it with a multiply. So that, I imagine, was the big insight, was see that multiplication is a very powerful operation. So we're just going to do x prime times some number m, and we're going to prove that there exists a number m that does what we need. So I'm going to write this out a little bit algebraically, so we can think about what m might be. Now x prime only has the important bits, so we can write that as a sum I equals 0 to r minus 1 of x bi 2 to the bi. So I'm introducing some notation here. X bi is that important bit bi 1 or 0? Okay, this is just a dereference of the bit vector, of the bit string. And so you multiply that by that position to the, this is binary definition of binary notation, right? But we only care about the important bits because only those are set. So that's x prime. And then we're multiplying that by m. Now m could have any bit set. So I'm going to write it like this. Is it really only R? Yes. I'm going to assume that M only has R bits set, same as the number of important bits. R is the number of important bits. But I don't know where they are, so I'm just going to suppose they're at positions M0, M1, up to MR minus 1. So I've got to find what these MIs should be, or MJs. And now I'm just taking this product. So we can expand out the product algebraically and see what we get. So what's this product? Sum I equals 0 to R minus 1, sum J equals 0 to R minus 1 of XBI 2 to the, just the product of these. So 2 to the BI plus MJ. Okay, that's the algebraic product of those two things. That's why I wrote it out this way, so I can see what's going on. The point is, when you do multiplication, you're doing sort of these pairwise products. The guys that are going to survive are the ones where the XBIs are 1, of course. But they survive in multiple places. Essentially, the MJs shift all of those bits by various amounts. So it used to be at this position, 2 to the BI, but now we're shifting it by MJ for all J. So some of those bits might hit each other, then they add up. That's really messy. We're going to avoid that and design the MJs so that all of these values are unique. Therefore, bits never hit each other. That's step 1. And then furthermore, what we care about, or what we're trying to do, is to get get the XBIs to appear in a nice little window, consecutive interval of W to the 4/5 bits, somehow by setting the MJs. So let me tell you the claim, which we will prove by induction. So we're given these BIs. That we can't control. Those are the important bits. And the claim is we can choose the MIs such that 3 properties hold. First one is that BI plus MJ are distinct for all I and J. So that was that these bits don't collide with each other. So there's no actual summation here. These sums could then be replaced by ORs, which makes it very easy to keep track of where the bits are going if we can achieve this property. Property B is that turns out the bits I'm going to end up caring about are B0 plus M0, B1 plus M1, and general BI plus MI. Right? In general, we have BI plus MJ for different values of I and J. I claim the ones I care about are the ones where I and J are equal. So I'm going to look at these bits, and in particular, I want them to appear in order in the bit string. Okay. And then third property, yeah, I need some more space, is that if I look at the span of those bits, so I look at BR minus 1 plus MR minus 1 minus B0 plus M0, that is the interval that these bits span, I want that to be order R to the 4th power, because R was W to the 1/5. So this would be order W to the 4/5. That's what I need for everything to fit in. So this is guaranteeing that these bits are the sketch that I need. Okay, they appear in order, and they don't span a very large interval, just w to the 4/5. This is what I need to prove. If I can prove this, I have approximate sketching. So let's prove it. Proof happens in 2 steps. First thing I'm going to worry about is just getting these guys distinct. Then I'll worry about the order property. So here's how we get them distinct. And these are going to be the mi primes, not quite the mi's that we want, but they're all going to be integers less than r cubed, greater than or equal to 0. And they're going to have the property that the bi's plus mj primes are distinct mod r cubed. So this is a stronger version of A. We really just need them to be distinct, but to make it easier for the other steps, we're going to force them to be distinct mod r cubed. Okay, how do we do this? By induction. So let's suppose that we've picked m0 up to mt minus 1. So suppose by induction that we've done that. And now our goal is to pick mt prime. Okay, so how do we choose mt prime? Well, what can't it be? Mt prime has to avoid basically mi prime, I believe minus bj plus b, I'm going to call it k, I guess so, different k, but if it avoids all expressions like this, then mt prime plus bj will be different from mi prime plus bk. In other words, all of these things will be distinct. So it has to avoid this modulo r cubed. If I can avoid all of these things, so this is for all ijk. If I can choose mt prime to avoid all those, then I'm happy. Because then these things will continue to be distinct, and then I apply induction. Okay, well, how many choices are there for I, j, and k? For I, there's, I guess, t choices. Because mi can be any of these, any of the previous values. For j, there's it's called r choices. For k, there's r choices. That's how many important bits there are. So the total number of choices is tr squared. But t here is always less than r. So this is going to be less than r cubed. So that means there's less than r cubed things we have to avoid, but I have r cubed allowable choices. I'm working modulo r cubed. So I just pick any one that avoids the collision. This is basically deterministic hashing in a certain sense. We are choosing these values deterministically to avoid collisions in this simple hash function. Okay, it takes time. It's going to take polynomial time to compute this thing, and you can imagine if you just plug in hashing, this will work with some probability and blah, 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 but I want to make it always work deterministically because we know what the xi's are here. All right, so we've avoided collisions. Just there's enough space, that's all. That was step 1. Step 2, this will solve property A, even modulo r cubed. Now we have a little bit of space. We're allowed to go up to r to the 4th, and now we just need to spread out these bits. So that's step 2. Basically, we're going to set mi to be these values that we chose plus this weird thing, w minus bi plus IR cubed rounded down to a multiple of R cubed. So I guess you could put this in parentheses if you want. Rough idea is we want to take mi prime plus IR cubed. Because these mi primes, they're all values between 0 and R cubed minus 1. Okay, we got everything working modulo R cubed. If we could just add IR cubed to each of these values, that will spread them out. Right? Because each of these values used to fall just in this tiny range IR cubed, so if we can move the next one to the next position, move the next one to the next position, and so on. Spread them out to the left by adding on multiples of R cubed, then that will achieve property B. Okay, the annoying issue here is we don't want to mess things up modulo R cubed. So we need to round things down to be a multiple of R cubed so that this is congruent to mi prime. That's what we want. We want it to stay congruent mod R cubed. Okay, well, why do we need to round down to a multiple of R cubed? We were adding on IR cubed. Well, it's not quite mi that we care about. It's mi plus bi. Those are the bits that we want to be nicely ordered. And so we kind of need a minus bi here, so that when we take mi plus bi, those cancel. Okay, but then bi is not a multiple of R cubed, so you've got to do this rounding down to R cubed. Also, negative bi is a negative number. We can't really deal with negative numbers because you can't go left of 0. So we have to add on this w just to make things work out. Okay, so it's a little messy, and I don't want to spend too much time on why this formula works, but I think you have the essence of what's working. This is just to avoid negative numbers. This negative bi is so that when you add it to mi, it cancels, and so you end up with this IR. You get these R cubed separations. In the end, let me draw a picture, perhaps, somewhere. In the end, if you look at the bit space, so this is W bits, and you divide it up into multiples of R cubed, all of the mi primes are over here. So these are mi primes. You don't know in what order or anything. They're just kind of randomly in there. You chose them pretty much arbitrarily. In the low end of the spectrum, so from 0 to R cubed minus 1. And then what we want is for x0 plus m0 to fall somewhere in this range. And then x1 plus m1 to fall somewhere in this range. And x2 plus m2 to fall somewhere in this range. Okay, if I do that, and it's weird because the bits are numbered from 0 to the left here, then I will have this property. Okay, and I claim this assignment does that. It's an exercise you can check that indeed xi plus mi will fall in this range. Okay, so this gives us property B. It also gives us property C, because we've been fairly tight here. There's R of these guys. And each R of these intervals of size R cubed, and so the total range of these bits is going to be R to the 4th. Okay, we started at x0 plus m0. We end at xr minus 1 minus plus mr minus 1. That's going to be somewhere here. But if you look at just that interval of bits, so there are more bits actually over here. Yeah, in particular because of this w bit part. This whole picture basically starts at bit w. And then there's all this stuff to 0. So this is a more accurate picture. You're doing this multiplication. The garbage happens here. We have no idea. Garbage happens here. We have no idea. Actually, garbage happens all over here. But what we know is that these bits are the bits we care about. these are the xi plus mi bits. If you look at xi plus mi, they give you xbi. Okay, they exist in other places, but these bits will have the important bits. Now the bits are also like all over everywhere else, but none of the bits hit each other, so these bits remain correct. Because nothing else collides with it. And so if I just mask out those bits, again, so I have to do another mask. I did one mask here. I did a multiplication. And then I have to do another mask. So why don't I write it over here? So we mask with, we AND with sum I equals 0 to r minus 1 of 2 to the bi plus mi. Those are these circled bits. So if we grab those things and then we shift right by, why am I writing x? Sorry, these are all b's. Too many letters. And we shift right by b0 plus m0 because we don't care about all those leading bits. So we shift this over to the left. We did the mask. Then we will just have the important bits, and they will occupy over here an interval of size at most, let's say, order r cubed, or r to the fourth, sorry. Clear? So this is approximate sketching. This is definitely a bit complicated, but it works. Let me review briefly. So our algorithm was simple. We have a bit string x. We just want to get the important bits and compress them to a thing of size r to the fourth. So first of all, we threw away all the non-important bits with this mask. That was easy. Then we just did an arbitrary multiplication. And we proved that there was a multiplication that avoided collision. So the sums basically turn into ORs or XORs. I mean, you never get two 1 bits hitting each other, so you don't have to worry about that. And we did that with the simple inductive argument. And then we also wanted the bi plus mi's to be linearly ordered, because we need to preserve the order of the important bits. We can't just permute them. And we needed them to occupy a small range. And we did that basically by adding ir cubed to each of them, but it was a little messier. We had to add w and blah, blah, blah. Okay? But in the end, we got our important bits to be nicely spaced out here by pretty much putting an r cubed in between each one. So those were our bi plus mi bits. They occupy this range of r to the fourth. We mask out all the rest of the garbage because this multiplication made a quadratic number of bits. We only want these r bits. There are r squared 1 bits in here. Mask away all the others. Take these bits, shift them over. Now they occupy a nice interval at the beginning. Size order r cubed, r to the fourth. And that's our approximate sketch. So sketch should only take r, but we're being sloppy. I mean, with this multiplication trick, the best we know is to get down to r to the fourth, and that's good enough. And that's why I set everything to w to the 1/5, because this is w to the 4/5. We're going to have w to the 1/5 of them. And so if you take these sketches and you concatenate them, fuse them together, if you will, and that's fusion trees, then the sketches of all of the keys x0 up to xk minus 1 will occupy order 1 words, because it's ordered w bits. W to the 4/5 times w to the 1/5. Okay? Which brings us to parallel comparison. I have all of these approximate sketches, so you could start forgetting approximate sketching. Somehow we get these w to the 4/5 bits. We want to concatenate them together, and then in parallel compare all of them to the sketch of Q. Okay, the sketch of the xi's we can pre-process. We can actually spend a lot of time finding the sketch function. But then we have to fix the sketch function. We have to be able to compute sketch of Q in constant time. That's what we just did. Sketch of Q is one and, one multiplication, and another and. So computing sketches is fast. That's the steps, computing sketch of Q. Now, next step is find it among the sketch of the xi's. So this is the next thing we want to make fast. That's actually pretty easy. You probably know you can compare two integers by subtracting one from the other. So we're just going to do that, but in a clever way, so we can do k subtractions for the price of 1. I'm not sure. I'm going to define the sketch of a node to be the 1 bit followed by the sketch of x0 ... 1 sketch of xk minus 1. And I'm going to define sketch of q to the kth power, so to speak, to be a 0 bit followed by sketch of q ... 0 bit sketch of q. Okay, this is aligning things so that if I did this subtraction and this one, I would basically be comparing q with all the xi's at once. Okay, the point is, these sketches, this is the thing that fits in order 1 words. Right? These sketches are w to the 4/5 bits, and there's w to the 1/5 of them. So this whole thing is order w bits, so it fits in 1 word. This thing also. Okay, it happens to be the same bits repeated many times, but also fits in 1 word. How do I compute this thing? I can do it with a multiplication. It's sketch of q times 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. Okay, so ahead of time, I'll just pre-compute this bit string that has 1s at the rightmost slot for each of these k fields. If I just take that and multiply by sketch of q, then I get this. Okay, so this is easy to do in 1 multiplication. Now, I take this thing minus this thing. Take the difference. And the key thing is, because I put these 1 bits here, I'm taking this minus this. The point is, either this 1 bit will get borrowed when I do binary subtraction, or it won't. It gets borrowed when this is bigger than this. Otherwise, it doesn't get borrowed. So I'm going to get either a 0 or a 1 here, and then some garbage, which I don't care about, and a 0 or a 1 here, and then some garbage. And I'll just mask that out. I'm ANDing with 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. And so I end up just with the 0, 1 bits, and the rest zeros. Okay, and these bits, get it right, it's 1 if the sketch of q is less than or equal to the sketch of xi. And it's 0 if the sketch of q is greater than the sketch of xi. Because when it's greater, that's when the borrow happens, and then the 1 turns into a 0. So 1s indicate the query is too small, or they're just right, and 0s indicate that they're greater. Now, the xi's were in order. So probably x0 is too small, and so this bit will end up being a 0. Probably xk plus 1 is too big, so this bit will be a 1. In general, it's going to be a monotone sequence of bits. If you look at these bits, these 0, 1 bits, they're going to be monotone. They'll be 0 for a while, and then at some point they'll switch to being 1s. And that transition from 0 to 1s, that's what we want to find. These keys are too small, these keys are too big, this key is just right. So we fit between, this would be position I and position I plus 1, and we fit between xi and xi plus 1. Well, not actually xi and x plus 1. We fit between sketch of xi and sketch of xi plus 1. Okay? That's what we need to find. Now that is, again, the problem of finding the most significant 1 bit. But In this case, I don't need that operation. I can do it in a simpler way. But we're almost done, right? We've done all this parallel comparison. We just need to find that transition between zeros and ones. Turns out there's a cool way to do it. The cool way is multiply that word times our good friend, this thing. 0, 0, 0, 0, 0, 1. 0, 0, 0, 0, 0, 1. Okay, this is a little harder to think about, but take this bit string, multiply by this. Okay, what that does is it takes this string, it includes it because there's a 1 right there. It shifts it over by one field and includes it. Shifts it over by another field, includes it. So this repeats this thing. And now collision happens because they're perfectly aligned. If these 1 bits ever hit each other, they'll be summing. Now some of them are 0, some of them are 1. Instead of computing the position of the 0 to 1 transition, we could equivalently just count how many 1s are there. Because then that's counting from the right, whereas this is counting from the left, whatever. Same thing. So if I could count how many 1s, I'd be all set. And in this case, if you look at right here, this will be the number of 1s, I claim. Because if this 1 was there, it will stay there. And then all the other bits get shifted over and fall right here on top of this bit. So as they get added up, you'll get some carries and things will move over. But this is not very big because we're talking about k bits. So this is only going to be width log k. Okay, whereas this, there's tons of room here before we get to the next shift. Okay, so I just look at these bits, I mask them out, I shift them over, and that gives me the number of 1s. This is a cute way to count the number of 1s in a bit string when the bits are spread out nicely. They have to be at least log k away from each other, otherwise you get collision. This doesn't work for an arbitrary bit string, but for a bit string like this, we're all set. We can count how many 1s there are, then we figure out where this transition is. Okay? That is parallel comparison. One more thing to do, which is most significant set bit. Place we needed this was we were taking the XOR of Q with XI, and then we wanted to find the first bit where they were differing. So after you take the XOR, you've got some bit string that looks like this. You want to find this bit, because that's the place you diverged. Then we would turn that to 0 and change the rest to 1s. That's easy to do if we know where this bit is. And this is a generally useful operation. It's used all over computer science, I would say. So much so that most CPUs have it as an instruction. So on Intel it's called CLZ, and it has many names. They're in the notes. Most compilers provide this to you as an operation on architectures that have it. Otherwise, they simulate it. They probably don't simulate it as well as I'm going to tell you, because we're going to do this in constant time on a regular word RAM, just C operations, which does not seem to have made it into popular culture. It's slightly complicated, which is why. But what's cool is we're going to use, I'm going to do this relatively quickly because I don't have a ton of time. We're going to use all the things that we just did again, quickly. Most of them just as black boxes. All right. So here's what we're going to do. Maybe I should go somewhere new. So I'm going to use sketches, not approximate sketches, but I'm going to use sketches. I'm going to use multiplication. I'm going to use parallel comparison. And in some sense, I'm going to use most significant set bit. All of these things I'm going to use to solve the most significant set bit problem. So here's what we do. We split word into root W clusters of root W bits. Sound familiar? This is exactly what we did in Venom de Boas. Except Venom de Boas did this recursively. We're going to do it once. We can only afford constant time. So here's an example. X is 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1. Okay, so each of these is root W bits. There's root W of them. It can, it's approximate. It doesn't have to be exactly, but we'll assume X is a nice power of 2, so that works cleanly. All right. So the first thing, so what the high-level idea is, I need to find the first non-empty cluster. Here it happens to be the first cluster. And then I need to find the first 1 bit within the cluster. Okay? Hard part is finding the first non-empty cluster. Actually, the hard part, or the messy part, is finding which clusters are empty, which clusters are not. This cluster is not empty. This cluster is empty. These are not empty. So I want the summary vector, which is 1, 0, 1, 1. Claim if I can do that, everything else is easy. So let's spend some time on identifying non-empty clusters. Okay, first thing I do is I take X ANDed with this thing which I'm going to call F 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. F for first. So I'm just seeing which of these first bits in each cluster are set. So the result is I get 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, and 1, 0, 0, 0. So this is, in particular, that tells me this cluster and this cluster are non-empty. Duh, because they have the first bit set. What about all those other bits? Well, the other bits I'm going to do in a different way. Just the first bits, I need a little bit of room. I need this bit of room. I want to put these 1s in. Okay, so I've got to get rid of some bits to make room for that. So this deals with the first bits. Now I'm going to clear those out. So I'm going to take X XOR this. And that will give me everything with the first bits cleared. So I've got 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 1, 0, 1. Okay, these are the rest of the bits. I've got to figure out this one's not empty and this one's not empty. How do I do it? With subtraction. Okay, I take F minus that thing. This F has 1s, and they're going to get borrowed. When I take F minus this one will get borrowed because there's something here. This one will not get borrowed because this is 0. This one will not get borrowed because this is 0. This one will get borrowed because there's something here. That's it. Just we're comparing with 0. Everything. So we're going to get, in this case, 0 and some garbage, 1 and zeros, 1 and 0, some garbage. Okay, I just care about these bits. These are the bits that tell me which ones were empty. The zeros are empty, the ones are non-empty. Okay, so I do a mask. I get 0 and some zeros, 1 and some zeros, 1 and some zeros, 0 and some zeros. Okay, then I do an XOR with F, because I really want 1 for these guys and 0 for these guys. 1 means it's not empty, 0 means it's empty. Got that right? So I'm just inverting the 0 bits to 1 bits and vice versa. So 1 means this was not empty, 1 means this was not empty. Those are the non-empty guys. Okay, I take this and I OR it with this thing. Okay, this was the thing that told me which ones had the first bit set. So if I take the OR of those two, I learn, are any bits set? Because this was dealing with all of the other bits. I threw away this bit, but I had to remember that it was non-empty. Okay, so I take that OR. Now this tells me those 3 blocks were non-empty. This one was empty. So now here I have the bits that I care about. Sadly, they're spread out. I'd really like them compressed. So I do that with Sketch. I want to compress them to 1, 0, 1, 1. It would fit in one little thing here because this is root W. There's root W of them. Sadly, I can't use approximate sketch because I don't have enough space. This is W to the 1/2. If I used approximate sketch, I get W, I'd lose this factor of 4. It'd be bigger than W. I really need it to be perfectly sketched. Conveniently, you can do perfect sketch in this regime. Before, the BIs were arbitrary things. We had no idea how they were spread out. Here, BI is root W minus 1, that's the first one, plus I times root W. They're nicely uniformly spaced by I root W. In this case, run out of time, I claim you can use MJ equal to W minus root W minus 1 minus J root W plus J. And I won't go through the proof. There's a sketch in the notes. But if you do this, this is a nice setting of MJ. Turns out you will get BI. If we look at BI plus MI, this cancels because I equals J. You're left with W plus J. So in other words, if you look at BI plus MI, you get from bit W to bit W plus root W, I guess, minus 1. These bits will be exactly the bits you care about. So you take those, you mask out the others, you shift it over to the right, and you have exactly your perfect sketch. The thing you need to prove here is that BI plus MJ are all distinct, so there's no collisions. But in this case, it's easy to avoid collisions. Get all your bits nice and consecutive. Now you've got it down to this thing. Okay? Not quite done, though. One more minute. Say, well, that was step 1. Identify non-empty clusters. Step 2 was sketch. Step 3 is find the first non-empty cluster. I claim this is easy. So I take this sketch vector. It only has root W bits. So I use parallel comparison. What do I compare to? I'm going to compare many copies of this thing to 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, the powers of 2. Okay, so I take this, I put them in a vector like the sketch of a node, and I take the k, or I guess root W copies of the sketch of the summary vector. That's this 1, 0, 1, 1. So I compare 4 copies of this to each of these, and I learn which power of 2 it is greater than. In other words, what is the most significant set bit? That's why when I told you how to do over here, when I told you how to do parallel comparison, I didn't want to use most significant bit as a subroutine because this is a subroutine to most significant bit. Okay, over here we could just do this multiplication and boom, we found what the most significant set bit was, as long as there was room to fit all this stuff in a word. And because I've reduced everything to size root W, and there's root W of these things to compare to, because that's the width of one of these fields, this all fits in a word. I can do this parallel comparison. Boom, I find the first 1 bit in this bit string, which happens to be the first bit. That tells me that this cluster is a cluster I care about. So I take those bits out, I mask them out, shift them over, and I find the first 1 bit in that cluster. How do I do it? In exactly the same way. Cluster is, again, root W bits. I can use parallel comparison to compare it to all these things. In constant time, I find where the first 1 bit is there, and then it's, I take this cluster C, I take this bit D, and my answer is C root W plus D. That is the final index of the most significant 1 bit in constant time, using all those fusion tricks once again. And that, in the end, gives you fusion trees on a word RAM static. Whew. It's complicated, probably impractical, but pretty cool. And we're going to use these bit tricks again.